Hello, welcome once again to day 6 of Just Start Programming, the Rust programming language. Alright, so we're back. So let's do a quick review on what we have covered the other day. It was structs. So let's just quickly go through an example program using structs. So this was the example. So this is refactoring with tuples. And then here, instead of tuples, it's better to name your object as rectangle or your struct as rectangle, where you have width and height as the field. So then you can use it like this. You call a function to update the width and height of the rectangle like this. Adding useful functionality with derived traits. So if we print rectangle straight away like this, it will complain because rectangle doesn't implement display. So it doesn't know how to display the width and height properly, not unless if you do a dot notation, one dot width, something like this, and height. So according to the document, there is a way. You can do pretty print like this and this. But to do that, we need a few things. So we need to put in this, what do you call this one? What was this called? was it? Attribute. We add the outer attribute sharp enclosed in square brackets derive debug. Just before the struct definition. So just above struct, you add in something like this. And then here you can specify rect1, the variable rect1 colon question mark. And by doing that, it will show you the name of the struct and then the values of the field. Okay, so it's not the prettiest output. You can also do colon sharp question mark. So it will align it nicely. Like this one looks like JSON without the quotes. Another way to print out a value using the debug format is to have this debug macro. It's that. So you can do something like this. If you put it here, this line, once this line is evaluated, then it will show you the value without printing it out. And then debug exclamation mark will show you the pretty format also, like this. So from here onwards, let's try to use the debug macro instead. It's more user friendly. We don't need to put in so many things. We just use debug exclamation mark. Okay, so let's move on. I think the next topic would be quite interesting. Methods are similar to functions. We declare them with the fn keyword. Or maybe let's prepare our project first. Yeah. So here, go to projects, Rust, we do a cargo new methods. Methods, we do a tree, just to double check. So we have source and main. Okay. And then, okay, so this was from yesterday. Can save this and close this one. And from here, we can open Visual Studio Code by typing in code dot. Let's open up main.rs. And so let's try this one. It has a rectangle instance as a parameter for the area. So we're creating the area function that has a rectangle instance as parameter, and instead make an area method defined. So it's a method defined on rectangle. How can we do that? Struct rectangle, then okay, so impl rectangle. There's a function inside. Okay, let's copy this. Let's inspect this one. Okay, so rectangle is the struct. How do we know that area is a function of rectangle? Well, it's mainly because of this one. IMPL implementing functionality for a type. Primarily used to define implementations on types. Inherit implementations are standalone, while trait implementations are used to implement traits of types and other traits. Okay, so area is in rectangle. Then there's this, so we are borrowing what is self. So self is a parameter. It will return unsigned 32 scalar type. So self.width times self.height. Okay. Let's read the explanation and try to understand what's going on here. To define the function with the context of rectangle, we start an IMPL implementation. Block for rectangle. Everything within this IMPL block will be associated with the rectangle type. Then we move area function within IMPL curly brackets and change the first, and in this case, only parameter to be self. In the signature and everywhere within the body. In main, where we call the area function and pass rect1 as an argument, we can instead use method syntax to call area method on our rectangle instance. The method syntax goes after an instance. We add a dot, so it's a dot followed by the method name, parenthesis, and any arguments. Okay, in the signature for area, we use at self instead of rectangle at rectangle. The at self is actually short for self colon at self within IMPL block. The type self is an alias. Okay, so self is an alias for the type that IMPL block is for. Methods must have a parameter named self of type self. Okay, methods must have a parameter named self, this one, of type self. So self with a capital S is actually a type for their first parameter. So Rust lets you abbreviate this with only the name self in the first parameter spot. Note that we still need to use ampersand in front of the self shorthand to indicate that this method borrows self instance, just as we did in rectangle. Methods can take ownership of self, borrow self immutably, as we've done here, or borrow self mutably. So it's both, you can borrow immutably and mutably. So in this case, it's immutable. Yeah, it's immutable because there's no mut here. And here we did not put mut. Okay. We chose at self here for the same reason we use at rectangle in the function version. We don't want to take ownership and we just want to read the data in the struct, not write to it. If we wanted to change the instance that we've called the method on as part of what method does, we'd use @mut self here, @mut self as the first parameter. Having a method that takes ownership of the instance by using self as the first parameter is rare. This technique is usually used when the method transforms self into something else and you want to prevent the caller from using the original instance after the transformation. The main reason for using methods instead of functions, in the addition to providing method syntax and not having to repeat the type of self in every method signature, is for organization. We put all the things we can do with an instance of a type in one IMPL block rather than making future users of our code search for capabilities of rectangle in various places in the library we provide. So it's mainly for organization purposes, so that everything referring to the capabilities of a rectangle can be grouped under the rectangle struct. Note that we can choose to give a method the same name as one of the struct's field. For example, we can define a method on rectangle that is also named width. Okay, rectangle width. Okay, because width is a function name. Yeah, while width on the rectangle is the field name. That's how I understood it. So rect width. Okay. There's a small difference. If you see rect1 dot width is a function. How do we know that? Mainly because of the curly, no, not curly, but the parenthesis. While here, rect.width is referring to the field name. Okay, here we're choosing to make the width method return true. Okay, Boolean. If the value in the instance width field is greater than 0. Okay, width is referring to this. If it's greater than 0, so it's greater than 0, then it returns true. And false if the value is 0. Yeah, because this one, the condition will return the Boolean value. So if it's 0, then it becomes false. When you follow rect1.width with parentheses, yeah, this one, Rust knows we mean the method width. When we don't use parentheses, Rust knows we mean the field width. This one. So we just need to be careful. So if we are referring to the function, then it should be parentheses. If we are referring to the field, it should be width. Often, but not always, when we give a method the same name as a field, we want to only return the value in the field and do nothing else. Yeah. No operations. We just return the value of the field, nothing else. Methods like this are called getters. And Rust does not implement them automatically for struct fields as some other languages do. Getters are useful because you can make the field private, but the method public. Okay, getters are useful because you can make the field private, but the method public, and thus enable a read-only access to the field as part of the types public API. We will discuss what public and private are and how to designate a field or method as public or private in chapter 7. Where's the dash greater than operator? Where's that? Yeah, this one. In C and C++, two different operators are used for calling methods. You use dot if you're calling a method on the object directly, and dash greater than if you're calling the method on a pointer to the object, and need to dereference the pointer first. In other words, if object is a pointer, object dash greater than, yeah. So maybe this one is simple to read. It's like there's an arrow, so it's pointing to something. Okay, pointing to something is similar to which? Similar to this. Okay, so I think it's referring to C and C++, both of these uh, uh, pointer reference. Okay, in Rust, Rust doesn't have an equivalent to dash greater than operator. Instead, Rust has a feature called automatic referencing and dereferencing. Nice. Calling methods is one of the few places in Rust with this behavior. Here's how it works. When you call a method with object.something, Rust automatically adds in ampersand, mutable, or asterisk, so object matches the signature of the method. In other words, the following are the same. Okay, so P1 distance ampersand P2. Ampersand P1 dot distance ampersand P2. What is this? The first one looks much cleaner. This automatic referencing behavior works because methods have a clear receiver, the type of self. Given the receiver and name of a method, Rust can figure out definitively whether the method is reading at self, mutating self, or consuming self. The fact that Rust makes borrowing implicit for method receivers is a big part of making ownership ergonomic in practice. Okay, let's see. Methods with more parameters. Let's practice using methods by implementing a second method on the rectangle struct. This time we want an instance of rectangle to take another instance of rectangle and return true. The second rectangle can fit completely within self, first rectangle, otherwise it should return false. That is once we have defined can behold method. We want to be able to write a program shown in this thing 5-14. What is this? Let's run it from here. Can we run it from here? No. Copy this under main. It's main. Okay, here. Maybe let's run this one first. Right. Area of rectangle is 1,500 square pixels. Okay, let's replace main. Rect1 can hold. No method can hold. What do we get that can hold? Here. Okay, copy this. Put it here. When we're creating function, do we need a semicolon? Function? No, it's not needed. Okay. Let's run this. Rect1 can hold rect2. True. Can rect1 hold rect3? False. Rect1 can hold rect3. What happened? Can hold is a function, self, and then other rectangle, boolean. If self width is greater than other width, okay, so there are two rectangles. Self is this rectangle, greater than another rectangle, and self height is greater than other dot height. So it means can hold means the width and height. So here rect2 is 10 and 40. So rect1 is 30 and 50. So 10 is greater than 30 is greater than 10, so it can fit the width, and 50 is greater than 40, so this is true, which is correct. And then here 30 is not greater than 60, so that is already false. Let's see what's the condition. And so I think once this is false, everything is false. But let's check. 45 is less than 50. Yeah, this is true, but because of this one is already false, then this one should be false. Okay, so let's try using the debug macro. Let's see if we can put it here, dbg, because we wanted to see the output of this. Oops. This. And then here, dbg. See? Run. Okay, so this is just a warning, dead code, meaning area was not used anywhere. Okay, here self.width greater than width equals true. Okay, I think this is for the rect1 and rect2. So both true and true. Can hold rect2 true. But for rect3, so first self-width greater than other width is false. So you see it did not evaluate the second line. Can rect1 hold rect3 greater than question mark? False. Can we do something like debug also here? Debug. I wanted to display rect 1. Rect 2. Okay, so let's just add one line since I don't know how to format this yet. Value moved here. Move occurs because rect1 has type rectangle, which does not implement the copy trait. Okay, because we already displayed it here. Okay, so let's borrow 1, borrow rect2, here borrow rect1, borrow rect2, rect3. So you can see the pattern. Every time we call something like a function, we just borrow it by having this ampersand sign. Okay, so let's run this one. True, because 30 and the other one is 10 and 40. False, false, because you have 30 here and the other one is 60. Okay, let's move on. I think that is already clear. Associated functions. All functions defined within IMPL block are called associated functions because they are associated with the type named after IMPL. So it's associated to area is associated to rectangle, can hold associated to rectangle. IMPL, rectangle. Struct, rectangle. We can define associated functions that don't have self as their first parameter and thus are not methods because they don't need an instance of the type to work with. We've already used one function like this in string from. It is defined on the string type. Associated functions that aren't methods are often used for constructors that will return a new instance of the struct. Okay, so here they mention constructor. These are often called new, but new isn't a special name and isn't built into the language. For example, we could choose to provide an associated function named square that will have one dimension parameter and use that as both width and height, thus making it easier to create square rectangle rather than having to specify the same value twice. Okay. Yeah. So for rectangle to be square, it means that the width and height are the same. So what was done here is there's a function square and then size as the parameter and sine 32, returning self. So since self is a type, so self is returned with the size and height same as size. So it's a square. The self keywords in the return type and in the body of the functions are aliases for the type that appears after the IMPL keyword, which in this case is rectangle. So self is an alias for the type that appears in the IMPL keyword. So I think we can remove self and put in rectangle. I think that should be fine since it's an alias. Okay, let's do that. Let's verify our guess. So it's a guess. Copy this. Let's add it here. Let's put a space here. So it should be fine. Square is not used anywhere. We can do something like, let's add that square but rectangle equals rectangle. So instead of putting in the width and height, dot square square. Let's put 10. And we can display debug. Printing anything anymore. We'll use debug instead. Square 1. Okay, what is wrong? It's like string, column, column, square. No wonder it did not show up. Okay, so slight difference, as you can see. Method is called dot, but square here appears to be okay, colon colon is a constructor. Okay, so that's my guess. Let's see. 10 and 10. Okay, but what we wanted to prove is, since self is an alias, why not we place this with rectangle and see? Anyway, we know it should be rectangle. Yep, so far it did not complain. Let's run this one. So it's fine. Let's put it back. So then what else can we observe here? So size, but not referencing. We're not referencing, so it's copying. It is copying. Copy. Size 10. Why we don't have ampersand here? Okay, what will happen if you put ampersand? Size should still be fine. Error. What is the issue? Move ampersand to the type. Okay. Okay. So the difference is self here is actually rectangle, while size is referring to not to the rectangle, but it's being used here. Okay, so let's remove this. Is that correct? Because size is U32. Okay, so not unless if we, no. Is it possible to have something like this? Is that valid? Like that? Type parameter size by reference. Move ampersand to the type. Ampersand to the type. This one. Consider introducing a named lifetime parameter. Okay, so I think that would be in the future chapters. Okay, so in the meantime, let's just remove this. Okay. Let's proceed. Okay, to call this associated function, we use colon colon. So this is an associated function. With the struct name, let SQ equals square, like this. That's what I did here, except the value is 10. Because if we change this to dot to complain, yeah, and we don't see square anywhere, yeah, use the path separator to refer to an item. Quick fix. There. So colon colon means an associated function. And it looks like a constructor also, rectangle. Because it is returning self, which is a rectangle here. Okay. Syntax is used for both associated functions and namespaces. Okay, so colon colon represents associated functions and namespaces created by modules. I think that would be chapter 7 over here. We'll discuss modules in chapter 7. Okay. Multiple IMPL blocks. Each struct is allowed to have multiple IMPL blocks. For example, you have rectangle area, and here you have rectangle can hold. Oh, so you can separate it. Okay, but what purpose? Probably organizing. There's no reason to separate these methods into multiple IMPL blocks here, but this is a valid syntax. We'll see a case in which multiple IMPL blocks are useful in chapter 10, where we discuss generic types and traits. Okay. Chapter 10. Generic types, traits, and lifetimes. Oh, I think the most complex part would be here, I assume. Okay. But for now, no one is stopping us to have multiple IMPL and with a function inside. But can we have associated function in here? It was not stated, but let's assume it is allowed. Okay, so let's try that one. So anything that's not here, we try it out and let's see. Okay, so let me copy this maybe. Let's copy this. If they are both the same, will it complain? Yeah, it will complain. So what we'll do, we'll remove this, or maybe remove this one. No, remove can hold. We have function square, so it can't be in both places. Oh, so it's possible. Rectangle, rectangle. Area can hold. Square is here. But you cannot have both. I'm just curious. Can we do something like another square here and instead of size U32, maybe we can explicitly put size 2 U32 size and size 2. Complaint. Why? Duplicate definitions with name square. Definitions for square. Other definition for square. Okay, so it's duplicate, but cannot do this. I mean, I want square with 2 parameters. So it's not allowed. It's not allowed. So it means you have to specifically put another function name. Square 2. Just ignore the naming convention. Square 2, yeah, so this is allowed, but cannot have x. So square. Is it allowed? Did I save it? Yeah, it's not allowed. We don't know why. I don't know how to make this possible later on. For now, let's just assume, let's just accept it's not allowed for now. Okay. Summary. Structs lets you create custom types that are meaningful for your domain. By using structs, you can keep associated pieces of data connected to each other and name each piece to make your code clear. In IMPL blocks, you can define functions that are associated with your type, and methods are kind of associated functions that let you specify the behavior that instances of your structs have. But structs aren't the only way you can create custom types. Let's turn to Rust enum feature to add another tool to your toolbox. Okay. Yep, so enums and pattern matching. This chapter will look at enumerations, also referred as enums. Enums allow you to define a type by enumerating its possible variants. First, we'll define and use an enum to show how an enum can encode meaning along with data. Next, we'll explore a particularly useful enum called option, which expresses that a value can be either something or nothing. Then we'll look at how pattern matching in the match expression makes it easy to run different code for different values of an enum. Finally, we'll cover how the if-let construct is another convenient and concise idiom available to handle enums in your code. Uh, I think for match, we did that during the first day. Let me try to see. First day, what was that? Hello world or guessing game? I think guessing game. Guessing game. Source. Game. So here, match. Let guess U32 equals to match guess trim parse, and then we have okay and error. Yeah. And then there's also this match guess compare secret number. So you can have ordering less, ordering greater, ordering equal. Print line, you win. I think ordering would be, yeah, ordering is here. It's like another standard library where we have the comparison. I'm not sure if match is, okay, I think match is a reserved word. So it doesn't have to be under ordering. Match is also here. Okay, let's see. Defining an enum. Where structs give you a way of grouping together related fields and data, like a rectangle with its height, width and height, enums give you a way of saying a value is one of possible set of values. For example, we may want to say that rectangle is one of a set of possible shapes that also includes circle and triangle. To do this, Rust allows us to encode these possibilities as an enum. Okay, let's look at a situation we might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work with IP addresses. Currently, two major standards are used for IP addresses. Okay, version 4 and version 6. Because these are the only possibilities for an IP address that our program will come across, we can enumerate all possible variants, which is where enumeration gets its name. Any IP address can be either a version 4 or version 6 address, but not both at the same time. That property of IP address makes the enum data structure appropriate, because an enum value can only be one of its variants. Okay, very important. An enum value can only be one of its variants. Both version 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type, and the code is handling situations that apply to any kind of IP addresses. We can express this concept in code by defining an IPADDR kind enumeration and listing the possible kinds an IP address can be, V4 and V6. These are the variants of enum. Okay, so here enum IPADDR kind, you have V4 and V6. Okay, so this one looks like just some labels. There's no data type tied to it. Let's see. IP-ADDR kind is now custom data type that we can use elsewhere in our code. Okay, so it's a data type on its own, custom data type. Enum values. We can create instances of which two variants of IP-ADDR kind like this. Let for IP-ADDR kind v4, 6 IP kind v6. So what is happening here? Note that the variants of the enum are namespaced under its identifier. Okay, so associated function or namespace. That's the meaning of the double colon. And we use a double colon to separate the two. This is useful because now both values, okay, let's call this v4 and let's call this v6, are of the same type IP address kind. We can then, for instance, define a function that takes any IP address kind. Okay, function route IP kind, IP address kind. Okay, and we can call this function with either variant. Route, so it can be v4 and v6. I see. Using enums has even more advantages. Thinking more about our IP address type, at the moment, we don't have a way to store the actual IP address data. We only know what kind it is. Yeah, true. We only know what kind it is. Given that you just learned about structs in chapter 5, you might be tempted to tackle this problem with structs as shown in listing 6-1. Okay, let's see. IP-IDDR kind, then you have a struct kind, IP-ADDR kind, so you're creating home. It's a v4 kind, and then there's a string. Loop back, a v6 kind, and then you have, okay, so this is a slice. So from starting to, is it a slice? Is it a slice? Has address, colon, colon associated with it. Use struct to, is it a slice? I didn't say. Let's revisit slice once again. No, slice is dot dot. It's not a slice. What is it? And has address colon colon 1. It's a value. Okay, it's a value colon colon 1. Associated with it. We've used a struct to bundle the kind and address values together. So now the variant is associated with the value. Let's just take a look. I didn't know that. IPv6 loop back. Yeah. So instead of 0 colon 0 all the way to 1, so it's represented as colon colon 1. Okay. Good. However, representing the same concept using just an enum is more concise. Rather than an enum inside a struct, we can put data directly. We can put data directly into each enum variant. This new definition of IP-ADDR enum says that both v4 and v6 variants will have associated string values. Okay. Okay, so this is where we can put value. So it looks a bit different. Enum IP ADDR B4 is a type, and it has a string data type, compound type. We attach data to each variant of the enum directly. Okay, so if this is a data type, does it mean we can have struct here as well? Possibly. We have an enum with a variant that takes in a struct data type. Most likely that's possible, but we'll see. It takes a string argument and returns an instance of ADDR type. We automatically get this. Okay, we automatically get this constructor function defined as a result of defining the enum. Okay. So if we read this one, IPADDR, okay, it's not associated function, but it's an enum type that takes in this value. And if we read string is data type, maybe. Okay, from is an associated function with this value. Can we check string? Okay, let's try to view, for example, we don't have string here. Maybe let's open up a new project. So we have now methods, maybe cargo new enums. Enums code dot. Can close this one. Copy this. Then let's check string. Let me open up string. String, okay. Let's look for from. UTF. UTF. Let's save. and and from implementation string inline. Okay. Yeah. So it's an associated function, I suppose. Okay, let's continue. So we can do something like this. There's another advantage to using an enum rather than struct. Each variant can have different types and amounts of associated data. Okay, so this one looks like a tuple. And then, yeah, a string. Enums handle in this case with ease, so this is possible. But if we use struct, then we need to define maybe IP1, IP2, IP3, IP4. We've shown several different ways to define data structures to store version 4 and version 6. However, as it turns out, wanting to store IP addresses and encode them, and encode which kind they are so common that the standard library has a definition we can use. Okay. Let's look at how standard library defines IPADDR. It has exact enum and variance we define and use, but it embeds the addresses data inside the variance in the form of two different structs. So yeah, so my guess is right. So there's a struct like this, and we put it here, which are defined differently for each variant. This code illustrates that you can put any kind of data inside enum variants, okay, or structs, for example. You can even include another enum. Oh, so an enum within enum. Also, standard library types are often not much more complicated than what you might come up with. Note that even though the standard library contains definition for IP address, we can still create and use our own definition without conflict because we haven't brought standard library's definition into our scope. We'll talk more about bringing types into scope in chapter 7. Okay, so let's see. Message can have quit, comma, move, write something, change color. A message enum whose variants each store different amounts of types of values. So a message of a quit variant, a message of a move variant, a message of a write variant, and a message of a change color variant. Quit has no data associated with it at all, so it's like our V4 and V6 earlier. While move has name fields like struct does. So it's like a struct. So it's like an inline struct. Just like a struct. Okay, so does it mean that we can create an inline struct? Let's see. Let's try that one out. So this one, it says it looks like a struct, but can we put location? Allowed. Error. Expected comma. So we cannot do that. We cannot do that. Can we put struct? Just guessing. If it's allowed. Okay. Okay. So it's not allowed. Okay. Let's remove that. Can I do something like it was already known that we can put in struct in there. Location. Then here we have x. Let's do I32, yeah, comma y I32. And then here point and point, put in location. Okay, so that is allowed because it looks like this. Can we do? Yeah, I think my syntax was wrong. So if we do something like this, oops, this practice so a bit annoying for Visual Studio. Okay, send it out. Can we put struct? No, allowed. Okay, so apparently it's not allowed. So we cannot do something like that. Okay. Defining enum. Okay, so quit unit struct, then move message can be like this. Tuple struct, unit struct, tuple struct. Okay, so for struct you can also have something like a tuple. But if you use the different structs, each of which has its own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message defined in 6-2. In this case, we are using struct versus enum. So what is the advantage? If we use the different structs, each of which has its own type, we couldn't as easily define a function. Okay, because if we pass this to a function, then eventually you are passing different. You would need to define different functions for the different struct data types. But if you use enum, then you'll just pass in message. Okay, so let's see. There's one more similarity between enums and structs. Just as we're able to define methods on structs using IMPL, we're also able to define methods on enums. So you can define methods on enums as well. Here's a method name call that we could define on our message enum. Message call. Okay, so since it's a function, self is an alias. Self is an alias to the message enum, and the ampersand represents something we're just borrowing. Okay, so message colon colon. So colon colon is associated function or a namespace. And then you have a write. Oh, this one doesn't have a write function. String from hello, and then you do an m call, or maybe it's just to demonstrate that you can call this function. But self is okay, so this one, it's not a constructor because there's no return to self, but it is a method. Okay, so that's why we have that call parenthesis. Let's look at another enum in the standard library that is very common and useful, option. The option enum and its advantages over null values. This section explores a case study of option, which is another enum defined by the standard library. The option type encodes the very common scenario in which a value could be something or it could be nothing. For example, if you request the first item in a non-empty list, you would get a value. If you request the first item in an empty list, you'll get nothing. Expressing this concept in terms of the type system means the compiler can check whether you've handled all the cases you should be handling. This functionality can prevent bugs that are extremely common in other programming languages. Programming language design is often thought of in terms of which features you include, but the feature you exclude are important too. Rust doesn't have the null feature that many other languages have. Rust doesn't have the null feature. Null is a value that means there's no value there. In languages with null, variables can always be in one of two states, null or not null. In his 2009 presentation, Null references the billion-dollar mistake. Tony, where? To pronounce that properly. I will look it up later. The inventor of null has this to say. I call it my billion-dollar mistake at that time. I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all use of references should be absolutely safe, with checking performed automatically by the compiler, but I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably cost $1 billion of pain and damage in the last 20 years. Okay, so he was the inventor of null. The problem with null values is that if you try to use a null value as a not null value, you get an error of some kind, because this null or not null property is pervasive. It's extremely easy to make this kind of error. However, the concept that null is trying to express is still a useful one. A null is a value that is currently invalid or absent for some reason. Problem isn't really with the concept, but with the particular implementation. As such, Rust does not have nulls, but it does have an enum that can encode the concept of a value being present or absent. The enum is option. Okay, so less than t, greater than, and is defined by the standard library as follows. enum option T. So it's an enum, either none or some. T. The option T enum is so useful that it's even included in the prelude. You don't need to bring it into scope explicitly. Its variants are also included in the prelude. What's a prelude? But let's just accept this information for now, that this is how it looks like. You have a T, none, and some as the enum type. Okay. You can use some and none directly without the option. Option colon colon prefix. The option T enum is just a regular enum, and some T and none are still variants of the type option T. The T syntax is a feature of Rust we haven't talked about yet. Yeah, that's correct. It's a generic, okay, so it's a generic type parameter, and we'll cover generics in more detail in chapter 10. For now, all you need to know is that T, okay, so T is what? Generic type parameter. Means that some variants of the option enum can hold one piece of any type, one piece of data of any type. So probably that's where the term generic type parameter comes from. And that each concrete type that gets used in place of T, okay, so if you want to have a concrete type in place of T, makes the overall option T a type of different type. Oh, that's a bit confusing. Here are some examples of using option values to hold number types and card types. Okay, let some number equals sum 5. So you don't need to specify option colon colon. That's what they say. But let's try it out. Let's try it out. Where shall we put it? Maybe here. Yeah. And here. There's an error here. Maybe let's connect this out for now. Some number. So some number, yeah, this is Visual Studio Code. I did not type this in. It will look a bit different from normal view. Save it again. Here. So I think we can type in option column. There's nothing wrong with that. But it says that we don't need to do that. So let me remove that one instead. Okay, sum 5. Sum car, sum E. Okay, so 5 is integer, signed integer 32. Then here it's a character. So it's like, yeah, sum would depend on, okay, option becomes whatever T is. It can be character. In this case, it is character. In this case, it's a number. Absent number, option I32, none. We'll hold by looking only at a non-value. Here we tell Rust we need absent number to be of type option I32. Okay. Why, if I uncomment this, why does it complain? Standard option, option underscore, and option I32 have similar names but are actually distinct types. STD option underscore is defined in crate core, and option I32 is defined in the current crate. So this is okay, so I think it's confused. STD option underscore. Can we do something like STD option? Yeah. So now it's okay. Yeah. Can do it like this. Okay. When we have some value, we know that a value is present and the value is held with some. When we have none value in when we have non-value in some sense, it means that the same thing as null. Don't have a valid value. So why is having option T any better than having null? In short, because option T and T, where T can be any type, are different types. The compiler won't let us use an option T value as if it were definitely a valid value. For example, this won't compile because it's trying to add an I8 to an option I8. So X, okay, so it's an I8 integer, signed integer, 8-bit, 5, and Y is option sum 5. Let sum equals X plus Y. Why did it complain? If we run this code, we get an error message like this one. Cannot add, yeah, because option is an enum to a data type I8. No implementation for I8 plus option. Okay, not implemented. Intense. In effect, this error message means that Rust doesn't understand how to add an I8 and an option I8 because they're different types. When we have a value of a type like I8 in Rust, the compiler will ensure that we will always have a valid value. We can proceed confidently without having to check for null before using that value. Only when we have an option I8 or whenever type of a value we're working with, do we have to worry about possibly not having a value. And the compiler will make sure we handle that case before using that value. In other words, you have to convert an option T to a T before you can perform T operations. So T is I8, so you have to convert it into I8 before you can perform I8 operations. Generally, this helps catch one of the most common issues with null, assuming that something isn't null when it actually is. Okay, but how do we check? Eliminating the risk of incorrectly assuming a not null value helps you to be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type option. Then, when you use that value, you are required to explicitly handle the case when the value is null. Everywhere that a value has a type that isn't an option T, you can safely assume that the value isn't null. Okay, so you can safely assume that the value isn't null. So whether it's I8, U32, or what have you, if you don't have this option enum, then you can safe to assume that it isn't possible for it to be null. This was a deliberate design decision for Rust to limit its null pervasiveness and increase the safety of Rust code. So how do you get the T value of a sum variant when you have a value of type option? So then you can use that value. Enum has a large number of methods that are useful in a variety of situations. You can check them out in its documentation. Okay. Becoming familiar with the methods of option T will be extremely useful in your journey with Rust. In general, in order to use option T value, you want to have code that will handle each variant. You want some code that will run only when you have some value, and this code is allowed to use inner T. You want some other code to run only if you have none value. That code doesn't have a T value available. The match expression is a control flow construct that does this when used with enums. It will run different code depending on which variant of the enum it has, and that code can use the data inside the matching value. Okay, so let's move on to match. Let's see, how can we check if you have some or if you have none. Okay, the match control flow construct. Rust has an extremely powerful control flow called match. Okay, maybe what I can do, let's save this. And then let's create another project. Cargo new match. Oh, it's a Rust keyword. So how should we? Okay, match control flow. Okay, code dot. Okay, so let's see. Match. Compare value against series of patterns. Execute based on which pattern matches. Patterns can be made up of literal values, variable names, wildcards, and many other things. Chapter 19 covers all the different kinds of patterns and what they do. The power of match comes from the expressiveness of the patterns and the fact that the compiler confirms that all possible cases are handled. Think of match expression as being like a coin sorting machine. Coins slide down the track with variously sized holes along it, and each coin falls through the first hole it encounters that it fits into. In the same way, values go through each pattern in a match. And at the first pattern the value fits, the value falls into the associated code block to be used during execution. Speaking of coins, let's use them in example using match. We can write a function that takes an unknown US coin and in similar way as a counting machine determines which coin it is and returns its value in cents as shown in 6-3. Okay, so we have enum coin, penny, nickel, dime, quarter, and then you have a function value in cents, coin, match coin as the variable. Okay, match coin. And then you have coin as an enum, coin, namespace, penny. Okay, this one, what is this? This one, you know, it's return, but we don't know what this is. So maybe let's check over here. Let's break down the match value in cents function first. Use the match keyword, value coin. Okay, this seems similar to a conditional expression used with if, but there's a big difference. With if, the condition needs to evaluate to a Boolean value. Yeah, if is Boolean. But here it can be any type. It can be any type. So coin here is an enum. The type of coin in this example is coin enum that we define on the first line. Next are the match arms. Match arms. Okay. An arm has two parts, a pattern and some code. Pattern and some code. The first arm here has a pattern that is the value coin penny. Okay. Coin penny. And then the equal less than operator that separates the pattern and the code to run. Okay, so meaning here could be the code block. In this case, if you have a value, then it's returning 1. It means coin matches penny would return 1. Okay. Yeah. Okay, yes. And the match expression executes. It compares the resultant value against the pattern of each arm in order. So it will follow this order. If that pattern doesn't match the value, execution continues to the next arm, much as in coin sorting machine, and have as many arms as you need. Okay. The code associated with each arm is an expression, and the resultant value of that expression in the matching arm is the value that gets returned for the entire match expression. You don't typically use curly brackets if the match arm code is short. Yeah, like this. No curly brackets. You must use curly brackets, and the comma following the arm is then optional. Okay, so if you use curly brackets, don't need to specify the comma. Anyway, I think if you mistakenly added the comma here, the compiler will show you some error. Okay, lucky penny. Okay, here it shows lucky penny, and then it will return 1. But still returns the last value of the block, 1. Let's try this one. And let's try this. Okay. And then let's call so value in cents is just your normal function. Your coin, specify a coin. So here you put let coin, which is a let's just put coin, which is a penny, coin penny. So this one will print, no, not print penny, but we can, let's not use print, but debug. We learned that we can show the debug value here, like this. It's faster. I mean, it's more convenient. And let's run this. Yeah, value in cents coin equals to 1. Okay, so let's change this to have a code block. This. And we change this with, okay. Let's run this. Yeah, so Lucky Penny was printed out here. And then this one is printed out as a debug. Okay. So if we added a comma here, it still works. So it's acceptable. So it's more consistent. You have comma here and you have comma for each arm. Yeah, each arm. But if you mistakenly added this, happen. A fat arrow. Expected fat arrow. So it's called fat arrow. It's interesting. Let's see. There is such a known term for it. Fat arrow in programming. So it's known as fat arrow symbol, which is used in various languages to define a concise single expression function or lambda. This syntax is commonly found in JavaScript and C#. Fat arrow. Okay. So in JavaScript, you have fat arrow. Okay. Patterns that bind to values. Another useful feature of match arm is that they can bind to the parts of the values that match the pattern. This is how we extract values out of enum variance. If you have to excuse me for a while, let me take a Alright, I'm back. Sorry for that. My throat is drying up. Okay. Patterns that bind to values. As an example, let's change one of our enum variants to hold data inside it. From 1999 through 2008, the United States minted quarters with different designs for each of the 50 states on one side. No other coins got state designs, so only quarters have this extra value. You can add this information to our enum by changing the quarter variant to include a US state value stored inside it, which we've done in 6-4. Okay, so enum, then okay, so quarter will have an enum of the US state. Let's imagine that a friend is trying to collect all 50 state quarters. While we sort or lose change by coin type, we also call out the name of the state associated with each quarter so that if it's one our friend doesn't have, they can add it to their collection. In the match expression for this code, we add a variable called state to the pattern that matches values of the variant coin quarter. When a coin quarter matches the state variable, will bind to the value of that quarter state. Then we can use state in the code for that arm like so. Okay, let's try to understand this one. So quarter will have a state, and then print state quarter from state. This is a pretty print. Quarter state. Okay, quarter US state. This. But how do we do binding of variable? If we were to call value in cents, okay, coin quarter US state Alaska. Okay, so here we also have namespace. So enum US state is an enum. Okay, right. Coin namespace quarter US state namespace Alaska. Coin would be Alaska. When we compare that value with each of the match arms, none of them match until we reach coin quarter state. That point, the binding for state will be value US state Alaska. Okay, so it could be Alaska or Alabama. In this case, it's Alaska. If you put in Alabama, then Alabama will be displayed here. You can then use that binding in print line expression. Okay. Matching with option T. Okay, in the previous section, we wanted to get inner T value. Okay, so this is now the application of the option where we wanted to extract the value T. Okay, let's say we want to write a function that takes an option I32. And if there's a value inside, adds 1 to that value. If there isn't a value inside, the function should return none value and not attempt to perform any operations. This function is very easy to write thanks to match. And we look listing 6-5 plus 1, so variable x takes in option I32, returns option I32, match x, x. So if it's none, then it will return none. If it's some, execute something. Oh, you can do it in line also like this. So let's try this out. This one should be somewhere. Sum 5. Okay, let's try to analyze it before we read the book, and let's see if our understanding is correct. Plus, okay, 5. So you have some value 5 and 6 plus 1. We are actually doing a copy, okay, because this is scalar type. So 5 copy to x, and x, we're checking, is it an option? Yes, it's an option. Does it match none? So it will skip none, but it will use sum I32. Okay, so I is here, so I32 plus 1. So plus 1, so plus 1 returns 6. Okay, but here plus 1 is none. Yeah, none is actually option none. To be more explicit, I think we can do something like option none. Okay, so 5. Okay, maybe here what we can do is debug 6. So that will print 6. I think I can do a pretty print. I remember, is this 6? And then something like this. What was that? Column. Question mark. 6. Okay, let's run it. Is this 6? Oh. What's wrong? Can we just do like this? No, 6. That is strange. I did not put any debug. Was it print line? Sidetrack a bit. Is this 6? 6, 7. Okay. sum 6. Yeah. So it was 6. Yeah, so this one was applied. I think we can put debug here as well. dbg, it will return option. I can just wrap it like that. Okay. So at sum plus 1, it is already 6. So that we don't need to print it here to see. Yeah. But if it's none, okay, maybe let's put debug here also. Debug none. And then let's run this. So it was 6, and then here it's none. Okay. None, sum plus 1. So I takes the value 5 here. So this is how we can extract the value. We can just easily not increment it and just return I. You can return I. But that is still an option, I would say. 6. This will return 6. Ah, okay. So 6 is not an option, it seems. Can we verify again? Oh, 6 is an option. But we are doing the plus operator here. But 6 is still an option. Can we try something? Let's move this a little bit here. Then let me create another function. Extract. This is what I wanted to do. Option I32. Slim arrow. No, I don't want option, but just return I32. Can I do that? Match X and none. Cut arrow. Debug. No, just return none. Then sum I32. Cut arrow. I'll just return I. Do that. Okay, it will not allow it, so we will not return option. So can I just, if it's none, I'll return 0. Make sense? Yeah. No, if it's none, I'll return 0. And here, comma, get a colon. Why? Ah, okay. Up, up, up. Yeah, there's an extra colon. Extra colon added by Visual Studio Code. This one makes more sense. So if I put let n equals extract x, so x would be 5. Debug n. So what I wanted to do is we have 5, which is an option. So I just want to extract the value of 5, t, which is I32 in this case. And if it's none, I'll just return 0. If it's there, then I'll just return the number itself. Yeah, n equals to 5. So what if instead of 5, this is sum? No, it's not sum anymore. What I'll do is option 1, or we can remove option. Just put in none. So it will be 0. Yeah, so I hope that is clear. Okay. Okay, so you don't need to read through that. You already seen it in action. Combining match and enums is useful in many situations. You'll see this pattern a lot in Rust code. Match against an enum. Bind a variable to the data inside and then execute code based on it. It's a bit tricky at first, but once you get used to it, you'll wish you had it in all languages. It's consistently a user favorite. Matches are exhaustive. There are one other aspect of match we need to discuss. The arms pattern must cover all possibilities. Oh, consider this version of a +1 function which has a bug and won't compile. Because option you have some and none. So if you miss out none, it will complain. We didn't handle the none case, so this code will cause a bug. Luckily, it's a bug Rust knows how to catch. If we try to compile this code, we'll get into this error. None not covered. Okay. To do. Oh. We'll do something like to do. Oh, let's try that one. It's interesting. So instead of 0, why not we put in to do. To do. And not yet implemented. Okay. To do, maybe can we override the message? I'm lazy. Oh, takes in string, literal string. Unimplemented. Oh, I was right. I was right. We can do something like that. So let's see. Not yet implemented. I'm lazy. Yeah. Let's remove two. Oh, oh. Yeah. So it says it is exhaustive. Catch all patterns and the underscore placeholder. Ah. So using enums, you can also take special actions for a few particular values. But for all other values, take one default action. Okay. Imagine we are implementing a game where if you roll a 3 on a dice roll, the player doesn't move. Instead gets a new fancy hat. If you roll a 7, your player loses a fancy hat. For all other values, your player moves, then the number of spaces on the game board. Here's a match that implements that logic. The result of a dice roll hard-coded rather than a random value. And all other logic represented by functions without bodies, because actually implementing them is out of scope for this example. Other. Okay, so other is it a keyword? Yeah, other. Note that we have to put the catch-all arm last because the patterns are evaluated in order. So it's something we need to remember. If we put the catch-all arm earlier, the arms would never run. Rust will warn us if we add arms after the catch-all. Rust also has a pattern we can use when we want to catch all, but don't want to use the value in the catch all pattern. So underscore. Okay. It's a special pattern that matches any value and does not bind to that value. So no, other is a chosen name. But ideally, if you want to catch everything, that would be underscore. I mean anything that doesn't matches 3 and 7. Instead of a variable named other. Okay. Yeah, so there was a variable. This example also meets the exhaustiveness requirement because we're explicitly ignoring all other values in the last arm. We haven't forgotten anything. Finally, we'll change the rules of the game one more time. Okay, so here, yeah, so this is just the implementation. Here we're telling Rust explicitly that we aren't going to use any other value that doesn't match a pattern in earlier arm. We don't want to run any code in this case. Okay, we don't want to run any code in this case. So this is like like a placeholder also. There's more about patterns and matching that we'll cover in chapter 19. For now, we're going to move on to the if-let syntax, which can be useful in situations where the match expression is a bit wordy. Okay, so another option is if-let. Okay, let's scan through. Yeah, so this one is, I think, short. Okay, so concise control flow with if-let and let-else. If-let syntax. Okay, let's see. Match, we already know. Sum max. Okay, this is max. Okay, so some value inside max so that we can use it here. Okay, and then yeah,
Other than that, we do nothing. Okay. Which is annoying boilerplate. Yeah, because we have to put this in. So what's our option? If let. So if let sum max equals config max. This looks confusing. If let. Okay, let's read. If the syntax if let takes a pattern and an expression separated by an equal sign. A pattern, an expression. Okay, pattern is, which one is pattern? This one. Expression is equal. I think this is the expression. Yeah, so it's like equal to config max. Okay, so the let here is usually if you have a condition, but let here is an expression which I think it's evaluated, and then the outcome is like your if statement. So if this is true, then here, this one will be printed out. Okay, let's see. If let block in the same way we use max in the corresponding match arm. The code in the if let block only runs if the value matches the pattern. Using if let means less typing, less indentation, and less boilerplate code. However, you lose that exhaustive checking that match enforces. Yeah. So we're not using match anymore. We're using if let. If let depends on what you're doing in your particular situation and whether gaining conciseness is an appropriate trade-off for losing exhaustive checking. So it's just a matter of being concise or it's a trade-off between being concise and then losing exhaustive checking. Okay, anyways, in other words, you can think of if let syntax sugar for as syntax sugar for match that runs code when the value matches one pattern and then ignores all other values. Can include an else with an if let. Okay. Okay, so if we have match like this, the equivalent is else. Yeah. I think this one is easier to read for me than full control. Yeah. Staying on the happy path with let else. Okay, so now it's let else. Let's see. US state. Implementation of US state enum. Okay, so it did not say. Could be a struct also. And then you have the associated function or the method. So it returns bool, match, self, Alabama. Okay. Oh, so we can convert it into if let also. Describe state quarter. Okay. Coin option if let coin quarter state equals coin if existed in so it's a combination. They're combining the use of if let and match. So match here is in the function itself, existed in, because we are returning 1900. Greater than equal. Yeah. year greater than equal. Greater than equal. So greater than, of course, 1819. So this is true. Else relatively new. Okay, so it's just to show if let and else is here. I think if let is something new. Last time we just did if, then condition, execute the statement, and then you have else. Okay. That gets the job done, but has pushed the work into the body of if let statement. We could also take advantage of the fact that expressions produce a value either to produce the state from if let or to return early. We could do similar with a match. So with a match, let state equals if let. So if let is here. If state existed, okay. So if let is used to produce a value or return early. Return none when this function is called. If not, then it goes on with this. Oh, you can also do let else syntax. Takes a pattern on the left side and expression on the right very similar to if let. Okay, let's inspect. Coin, quarter state coin, else return none. Let else. Where's the let else? Else is here. Okay. Let this one, else none. Yeah. So that will simplify this part. So if you have a situation in which your program has logic that is too verbose to express using a match, remember that if let and let else are in your Rust toolbox as well. We've now covered how to use enums to create custom types. It can be one of the set enumerated values. Option T. You have match and if let also. Your Rust programs can now express concepts in your domain using structs and enums. Creating custom types to use in your API ensures type safety. The compiler will make certain your functions only get values of the type each function expects. In order to provide a well-organized API to your users that is straightforward to use and only exposes exactly what your users will need. Let's now turn to Rust modules. Okay, so let's end here. We'll save the next chapter for the following day. I hope you guys have learned something also, same way as I did. I know this process is quite painful. Yeah. It's a way that with an open mind, we can learn to accept new information and see how far we can go. So at this point in time, I don't think we are confident to tackle a huge project. There is still a lot of things we need to cover. So we're now 6th, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Still a long way to go. Yeah. Just keep me company. I'm sure if I'm learning, you will learn something as well. So let me end here and thank you so much for watching. Thank you and goodbye.